A couple of announcements before I start the lecture. Could we settle down, please? Thank you. A couple of announcements. One is about the recitation tomorrow. Ali will not be here. I'll be giving the recitation. But I have to be in a meeting downtown until 4 o'clock, so I don't think I'll be able to make it here. So we'll have the recitation at 4:30, from 4:30 to 6:30, instead from 4 to 6. I've sent an email to this effect to you as well. The second is about the midterm. The midterm would be for 2 hours, from 2 p.m. to 4 p.m. on Thursday. The midterm would be held both in this room and an auditorium in the adjacent building called the Shapiro building. Everybody whose last name starts with the letter J or lower, or alphabetically lower, should go to the C.P. Davis auditorium. A to J or J to Z? Which is a good question. Let me just check my own email. At this point, I could. No, I never checked with Word. What did he do? Whenever it's going to show up. All right, last name up to the letter J, please report to C.P. Davis Auditorium, and everybody else come to this room. And there's a map that tells you where that auditorium is. This should be on your email. You should be able to look it up. The other thing is that Ali told me between classes that you're all having trouble as to what to read from the textbook, if at all. So what he's going to do today is send you explicitly all the sections that you have been responsible for. Instead of just giving you chapters that I've done, he will go one level less of granularity and tell you exactly what sections you're responsible for. So hopefully that will make your life a little bit easier. Tomorrow we will go through the sample midterm, and if you have any questions, I'll be more than happy to answer. I don't think we have a class after the recitation, so if it doesn't end by 6:30, this is more for CVN than for you. If it doesn't end by 6:30, I'll be continuing further to answer questions. All right? Okay. So let's start with the story of convexity. And so far we were down to this part where we had started working with the properties of convex functions. And we had stopped here in the morning. We said that if a function f is convex and differentiable, and I've somehow managed to find a local minimum for an unconstrained optimization problem, then I can find, then that point is indeed the global minimum for that unconstrained optimization problem. So we'll continue with convexity and hopefully get to quadratic programs. That's where we want to start things. The second property is that a function f, if it is twice differentiable, so here I'm assuming that the function is once differentiable, meaning that it has a gradient vector. Suppose I go one step further and assume that the function is twice differentiable, then that function f is convex if and only if its Hessian is positive semi-definite. In one dimension, what it means is that f is convex if and only if the double derivative, the second derivative of x at every point x is greater than or equal to 0 for every x. In one dimensions, typically we also have the definition of a domain. We don't want to define this function everywhere. I have defined it in all of Rn. For convex functions, that's not a problem, but it's easy to think in terms of domains. So let's just make a use of this property and see what we can say. If you look at the function fx, which is, say, 1 over x squared, and the domain in which I'm talking about is x strictly greater than 0. I don't care about this function when x is negative or 0. I'm only looking at the domain x greater than 0. And the question is, on this domain, is this function convex? If you plot it, this function looks like a steeper version of 1 over x, and clearly this function must be convex. Let's just try to prove this. So if you take the first derivative of this function, you end up getting minus 2 over x cubed. You take the second derivative of this function, you end up getting 6 over x to the 4. Yeah, and that's strictly positive for every x in D. And therefore, by this property, we know that the function is convex. So, in applications, what one does is typically one never tries to get into the situation of trying to prove that a particular Hessian is positive semi-definite everywhere. It's just too complicated, and it's typically useless in practice. So what you do is you use this property. You typically in practice one starts from this property. You break up a function f into elementary functions and see whether you can put together, when you can prove that each of these elementary functions are convex or concave, and then use that property to say whether the entire function is convex or concave. So here's an example. Let's look at the function f of x. Again, it's r1 to r1, which is, say, x to the power 4 plus log of x. Do I want that? No. Let's just say x plus log of x. Let's say 2x plus log of x for x strictly positive. And for those of you who don't, I routinely write log ln and log the same. So to be perfect, let's put it the natural log of x. If this is a function that you want to prove whether this is convex or concave, what you do is try to use that rule over there. Let's try to break it up into component functions. So here's one function. Let's call this f1 of x. This is my other function. Call that f2 of x. And alpha 1 in this case is 2, and alpha 2 in this case is 1. So I'm pretending as if my total function f of x is actually given by a combination of 2 times f1 of x plus 1 times f2 of x. And then I'm going to see whether each of these functions is convex or concave and try to use that rule. So what about the function f1 of x? That's linear. So it's both convex and concave. What about the function f2 of x? That's the function log of x, and it looks like this. Doesn't come down. That's what this function looks like. So it is concave, and let's just try to use our rule. If you take the first derivative of log of x, you end up getting 1 over x. You take the second derivative of 1 over x, which you end up getting minus 1 over x squared, which is less than 0 for every x which lies in the domain, which means that f2 is concave. So from this you end up concluding that this is concave. Now I'm going to pretend that this x actually is not a convex function but a concave function. If you take weighted combination of concave functions, you end up getting that f itself is concave. So in practice, this is how you would do it. You would not want to take the entire function. In this case, it's a very simple thing. You have these two functions, you can put them together and you can see what's happening. But when you have more complicated functions, try to break them down into smaller functions which are all look either convex or concave. Then use the rule that if you take positive linear combinations, you get the function of the same kind. The next property that we would also need, we'll just need it in the next slide directly, is that if you take a convex function, so if f is convex and alpha is some real number, and you look at the set S sub, or do I call it S? I don't even have this. Let's call it S sub alpha. These are all those points x such that the function value at the point x is less than or equal to alpha. So let's call this the alpha level set. So here's my convex function, f of x. Here's my level alpha. So I take the two endpoints. So this set here is S sub alpha. So it turns out that if f of x is convex, this implies that for every alpha in R, this set is convex. No matter which alpha you choose, if you look at all those points whose function value is less than or equal to alpha, then you end up getting that that set is convex. What about if the function is concave? What can we say on the other side? I want to make a similar statement there. What would I want to do? Greater than or equal to. So if I define, let's call it S hat of alpha, which is the upper level set, which is f of x is greater than or equal to alpha, then what happens? The set is convex or concave?
Convex.
Convex. There is no such thing as a concave set. There is only convex sets, but there are convex and concave functions. Okay? Why is this useful? We'll see in just a moment. In the next slide, we'll make this property is used in optimization quite a bit. But the other way is not necessarily true. That is, if you find a function f such that for any given alpha, this level set is convex, that doesn't mean that the function is convex. So implication doesn't go in both directions. Here's an example. So this function the drawing is not perfect, but you can sort of get a picture of what I'm trying to do here. If you define this as your function, then this function is clearly not convex. You can take 2 points. Here's a point, there's a point. The straight line joining them does not lie above the function. But no matter which alpha you pick, here's an alpha, there's an alpha, the level sets are convex. So it doesn't go the other way. Level sets convex doesn't mean that the function is convex, but if the function is convex, then the level sets are convex. The function, so it turns out that we are interested in these kinds of functions also, not just convex functions. We are also interested in functions who have level sets which are convex, and those are called quasi-convex functions. I don't think we'll have a chance to actually work with quasi-convex functions, but just keep in mind that it doesn't go the other way. That's just something that you should remember. For those of you who have seen convex functions, what extra thing do I have to add here in order to make it go the other way? Does anybody know? What do I have to do to write this implication go the other way?
If the x equals alpha for several x's, the derivative shouldn't change signs.
Okay, hold on a moment. I don't want to assume that the function is differentiable. I don't want to I want a general statement. So this statement here doesn't say anything about differentiability. So I want to make it equivalent without going to differentiability. Yes?
We have to add that the set S are connected.
Are connected?
Yeah.
But this is connected. All the S's are connected here. For any value of alpha, S of alpha is connected. And that's a counterexample to what you just said, right? Anyway, this is sort of going off in a tangent. If you're interested, I can tell you offline. But think about it. You have to work a little bit to make it go the other way. If it's differentiable, then what the gentleman just said is true. You can't change signs. But if it's not differentiable, then there is an easy way of still making it go the other way, but think of increasing dimensions. The problem has to be posed in a higher dimension for you to go the other way. All right. Why do I care about all these properties? I care about all of these properties because I want to solve convex optimization problems. So what kind of problems are convex? So here are the definitions. We're going to look at, I'm going to call a nonlinear program a convex problem or a convex optimization problem if it comes in one of those two varieties. The feasible set is always convex. of this nonlinear program, I have to somehow show that all the feasible points are going to be lying in a convex set. If I'm trying to minimize a function, then I want that function to be convex. Otherwise, if I'm going to maximize a function, then I want that to be concave. They're both really the same, because the negative of a convex function is a concave function. So if I'm trying to maximize this, this is the same thing as minimizing minus f of x. You go down into that state. But since we typically differentiate between minimization and maximization, it might be easier to remember it this way. Okay? So we started out with a nonlinear program which looks like this. A bunch of inequalities going one way, a bunch of inequalities going the other way, and a bunch of equalities. So what we want to do is somehow put conditions on these constraints so that this becomes a convex program. The condition that I have on convexity is simply that the feasible set should be convex. One way of making sure that the feasible set is convex is to use these level set ideas. I'm going to say that the function f of x must be concave if I'm looking at a maximization problem, should be convex if I'm looking at a minimization problem. That's easy. I want to make sure that every time I have a constraint of this kind, less than equal to type constraint, then that function gi, which comes on the left-hand side here, better be convex. Since this bi is a constant, it's a number, all x's such that gi of x is less than equal to bi is a convex set, if I assume that gi is convex. From the first statement over there, if f is convex, then the level set of S alpha, where all x is such that the function value is below a scalar quantity, that's a convex set. If I assume that gi is concave for all I that belong to this kind of a constraint, then by the green line over there, I know that all x's which satisfy that constraint is going to be a convex set. If gi is concave, then all x's whose function value is above a scalar quantity is a convex set. What about when I'm looking at equality? Every equality can be thought of as two inequality constraints, one going that way and one going this way. If I interpreted it that way, then I want the function to be concave. If I interpret this as this way, then I want the function to be convex, which means that if I have equalities and I want the problem to be convex, those better be equal, better be linear constraints. All equality constraints better be linear. Okay? So let's try to do an example, see how we work this out.
So for the concave function,
Yes.
even below the level set line,
Yes.
the set is still convex.
So the question is that if f of x, if f of x is concave, is this a convex set? No. Not necessarily. It's only above is a convex set, not below. Here's the counterexample. This is a concave function. Take alpha. You get this part up to this point, and that part starting there. That's not a convex set. Question?
If for whatever alpha vector, the x's such as f to x between alpha and vector, this set is convex, then f is convex.
Yeah, or another way, that's absolutely right, or another way to look at it is to think of it as a convex set in two dimensions. What you're saying is basically the same thing. You're saying two different alpha beta, so instead of looking at it, look at a convex set not in just x variables, but look at it in both x and alpha variables, and prove that that set be convex. Then it will work out to be right. Okay, so here's an example, and let's try to work through the example and see whether it will work out. So I want to maximize 2x1 plus log of x, x1 plus, or log of x2. Just make our lives simpler. We've already shown that that function is concave, therefore it satisfies this property such that x2 is greater than or equal to 3, x1 squared plus x2 squared is less than or equal to 7, 2x1 plus 7x2 is greater than or equal to 2, x1 plus 2x2 is less than or equal to 3. Let's say that is the problem that we are given, and we are asked whether this is a convex program. So we go through all of those and check whether things are right. So this one works out. Where's my green pen gone? Here it is. So that checks out because it's a max and the function is concave. Now this guy here is a greater than or equal to type constraint. It looks like this one here. It's got a constant on the right hand side and there is a greater than or equal to. And the rule says that whatever function stays on the left hand side of this inequality better be what? Concave. The rule simply wants it to be concave. Is that true about this one? Yes. So this is correct because it's a linear function, which implies that it's a concave function. Done. What about the next one? That looks a little bit tough. Let's skip that. Then we'll come back to it once we have done the rest of it. What about this? Again, the same story as that one. So I'm done because this is linear, which implies concave. What about this? This is a less than or equal to type constraint, and therefore our rule says that in order for it to be convex, in order for the optimization problem to be convex, what you have to make sure is that the left hand side constraint is actually convex. This is a linear function, therefore it works even as a convex function, so I'm done. Now this guy, what do I want this fellow to be according to our rule? Convex. Now let's see how we can prove that that's convex. It's a circle and therefore it's a convex set. Somebody else mentioned both are convex sets, convex functions. So one way of looking at it is that it's a circle, therefore the feasible set is going to be convex. Another way to look at it is look at two different functions. So here's what I'm going to look at this constraint. So I'm going to pretend that x1 squared plus x2 squared is actually an addition of two functions. One, f1 of the vector x simply defined as x1 squared. This f2 of the vector function simply defined as x2 squared. Each of those functions is convex. Because the function only depends on one variable, I might as well pretend the other variable doesn't exist. And therefore, when I'm talking about this function, this is a convex function, that is a convex function. I add them up, you get a convex function. Therefore, this is a convex constraint. So this is convex. And therefore, my optimization problem is a convex optimization problem. Now, one thing to remember is that all these conditions are simply sufficient. They are not necessary. They are. So when I define a convex optimization problem, I said that all I care about is that the feasible set be convex. Here I'm asking for something stronger. I'm saying that every constraint better give me a convex set. It's possible. Oh, there's one thing that is missed. So doing all of this, what we have done is we figured out that all x's that satisfy this is convex set, this is a convex set, that is a convex set, and that is a convex set. Now we just have to make one more step further. How can I conclude that the feasible set is convex? What is the rule that I'm using?
Intersection.
Intersection. So each of these is convex. The set of feasible points is the intersection of all of these sets. And I have a rule which says that if each set is convex, if I take its intersection, I'll get a convex set. And therein lies this little bit of a gap. The definition of convex optimization simply says that the intersection must be convex. I don't care about each of those sets. It's possible to have sets that are non-convex whose intersection is convex. But when I'm defining something as a constrained nonlinear program to be convex, I'm saying each of those components must be convex. So I'm requiring more here than up there. Why? Because checking to see whether the feasible set is convex is a lot harder than checking to see whether each of the constraints is convex. Typically, in applications, this suffices. In applications, one can work with this and not lose too much. But just keep in mind that all you care about is that the intersection be convex, not the individual constraints. All right. Now, I'm going to jump forward a little bit. Or should I? No. Okay. Let's not jump forward. We'll come to it when the time comes. So what have we done so far? Let me just keep a running tally of things because this is what this class is about. So far we've looked at nonlinear programs. And identified two kinds of nonlinear program. Unconstrained problems. And we sort of know what to do with them. Not completely. We know that if I want to minimize or maximize, I have to look for points that satisfy this equal to 0, and then check to see what happens to the Hessian. Is it positive semi-definite, negative semi-definite, what happens? So we sort of know what to do with it. The second story that we have just identified is that of convex programs. We really don't know what to do with them right now. All we know so far is that there is this beast called a convex program, and we sort of know how to recognize it by looking at the constraints. We do know that if it's an unconstrained problem, then local is global. So for the unconstrained case, we have this result that local minimum is global minimum, and if I'm trying to maximize a concave function, then local maximum is global maximum. For the constrained problem, I haven't told you what happens. So it turns out that the same thing is true for the constrained problem, but we don't really know what is the definition of the same thing exists for the constrained problem as well. However, we don't know what a local minimum is. For an unconstrained problem, I have told you what a local minimum is. For a constrained problem, I have to still define what it is. Once we've defined it properly, we'll see that the same result holds. So the next story that I'm going to talk about, and I'm going to keep this, try to show it on this side. The next category of nonlinear programs are something called separable programs. So here's what a separable program is. So we will call a function f of x separable if it is a collection of functions, each of which depends on only one variable. You can separate out that function in terms of the variables. So here's an example of a separable function. The function that we were working with, f of x equal to 2x1 plus log of x2. This is separable. It can be broken down into two pieces, each of which just depends on one variable. F of x is a summation of n different functions, each of which just depends on the ith variable. This function what can you say about this guy? Is that a separable function? Yes? No? Yes. I mean, it doesn't really matter. The fact that I have extra variables doesn't mean anything. I will call this, here's how I'll divide this. This will be my f1 of x1, and that will be my f2 of x2. The function itself could be many different things. The only thing I want to make sure is that variables don't multiply or sit in the same bracket. So here's another function. 2x1 plus x2 plus log of x1, x2. So somebody had mentioned multiply. What about this function? Is that separable? Separable. Why? Because this thing can be written as log of x1 plus log of x2. Well, there's a little bit of a subtlety here. Why? Is it separable, or at least some of you should have felt uncomfortable when I did that. What?
Combined x1, x2 should be greater than sir, x2 and x1 could be separately negative.
Could be separately negative. So when it was So the fact that it was not defined at 0, that's a problem with even x1, x2. The thing is that when it was written like this, the only thing I required was x1, x2 must be positive or non-negative if I define log of 0 as minus infinity.
You can take it out as the absolute values. You can separate them out as the absolute values of each of them.
Yes, you could do it that way, the absolute value of x1 and the absolute value of x2. So you can write this as the same thing as absolute value of x1 plus the log of absolute value of x2 and make it separable. How about this one? F of x is equal to 2x1 squared plus x2 squared plus the log of 3x1 plus 2x2. That is not separable. There's nothing I can do to break apart the variables, so therefore it's not separable. Okay. So that should make it clear as to what is separable function. So a separable nonlinear program, as one would expect, is simply a nonlinear program where anything and everything, all the nonlinear functions are separable. The objective is separable and the constraints are all separable. And when you have this kind of a symbol greater than less than, it means I don't really care about what sign comes in there. Only thing I care about is all the functions that are involved in the nonlinear program are separable. Why do I care about separable programs? Well, separable programs are very close to linear programs. If you think about a linear constraint, so let's look at this linear constraint. That is clearly separable. Any linear constraint is separable. The other nice thing about linear constraints is every individual function is only allowed to be a scalar times the variable. In a separable program, you're allowed to have more general functions. Instead of having just scalar multiplying the value, you're allowed to take more complicated functions. But it turns out that if you know how to solve linear programs, and particularly if you know how to solve linear program with integer variables, then separable programs are very easy to solve. So we'll talk about some of them, and then we'll show you how to solve that. Okay. One thing I forgot, which I should bring up right now, in this story of convex programs, was this problem that refers to the homework problem that you have to solve. So let's backtrack a little. We're going back to the story of convex programs, and we'll come back to it and see the case of what happens to this particular problem. So the problem that we want to look at is the following. You want to maximize some 2x1 plus 3x2 minus 3 times 2x1 plus 7x2 minus 3, let's say, subject to a bunch of linear constraints, ax less than equal to b. And we want to see whether a function like that can be solved using linear programming. So when we talked about linear programming, we had talked about replacing an absolute value constraint by 2 different variables, and then we had also identified a situation where we said, well, this would work, but this other thing, when you're trying to put a constraint where the absolute value is less than b, it works, but absolute value greater than b, it does not work. And now what we want to do is use this idea of convex programs to try to understand in a careful manner what can be done with linear programs and what cannot be. So it turns out that if you have a piecewise linear, so here's the rule that works. A piecewise linear convex constraint can be linearized. If you have a piecewise linear constraint, meaning, what do I mean by piecewise linear? This is a piecewise linear function. You can identify pieces over which the function is linear. The entire function is not linear, it's not a straight line, but you can identify pieces in which it is linear. So the absolute value of x, suppose I look at this function, what kind of a function is that? That function looks like this. So here's x, and here on the y-axis I'm plotting f of x. It has two linear pieces, that one, and it's convex. So absolute value of x is a piecewise linear convex function. Now I want to ask ourselves about that particular problem over there. I want to maximize this function subject to some linear constraints, and I want to say whether this can be linearized or not. So what about the function up here? Is that a convex function or a concave function? So we should probably split the difference. Some people are saying convex, some people are saying concave. So maybe it's neither convex nor concave. So let's try our trick. What are the things that we do know? Absolute value. We know that's a convex function. So if I don't worry about what happens to the rest of it, this guy is convex. I'm multiplying it by -3. What happens to the function? Becomes a concave function. What about here? What's this function? It's a convex function or a concave function. I'll choose it the way I like it. So this entire function is now a concave function. I'm maximizing a concave function. That's good. It's going to give me a convex optimization problem. Linear constraints means immediately gives me a convex feasible set. I'm trying to maximize a concave function over it. Everything's fine. So without even trying to figure out how this thing is going to be linearized, I know it can be linearized. I can solve it by linear programs. Why? Because the objective is concave and it's piecewise linear. If I open these pieces, I have to consider two different pieces, one where this is not negative and another where this is non-positive. In both of those pieces, this function becomes a linear function. Okay. Now, how do we solve this? So once we have reassured ourselves that at this point I can solve this using linear programming, that there won't be any problem, then I can introduce a new variable and just call this maximize sum alpha, such that here's what I want to do. But let's see, I'm not going to put the sign there, and you're going to help me figure out what sign I need to put there. Something alpha, ax is less than equal to b, and alpha free. So I'm introducing a new variable alpha. I'm going to maximize alpha subject to those constraints. And I want to make sure that when I solve this problem at the bottom, I get an answer which is equal to the top. So what kind of a sign do I want here? Less than equal to alpha or greater than equal to alpha?
Greater than equal.
Is everybody convinced that this should be greater than equal to alpha here? Less than equal to alpha or greater than equal to alpha? Okay, so there's enough of a confusion here. So let's try this. This quantity is less than equal to alpha. Let's say. What is the optimum solution of that? I would claim that the optimum solution of that is infinity. I don't really care what happens to the constraints. At the bottom, I just set alpha equal to infinity. Any number, any finite number on the left-hand side is going to be less than infinity. So this problem doesn't give me any information about that problem. And another way to think about it is, what am I trying to do? I'm trying to find an x for which this is maximized. Here, I'm trying to maximize alpha. So in order for this alpha to be something that is achievable there, I better find an x such that its value is greater than equal to alpha. I'm trying to push alpha up, but I really want to make sure that there is an x above it. There's an x whose value is greater than that alpha. Otherwise, that thing is useless. If I put it to be less than equal to alpha, then this alpha has nothing stopping it. It can just go off to plus infinity. So the question is greater than equal to alpha. So once I do that transformation, now how would I linearize it? Now the next step is to linearize it, but I know that I can linearize it because of what? This is a piecewise linear convex constraint. The left-hand side is concave. It's greater than equal to alpha. I can bring the alpha onto the other side. It will all become greater than equal to 0, which is a convex constraint. So I can linearize it. I know I can linearize it. The question is, what is the explicit linearization?
One quick question. If that was positive 3 instead of negative 3, would you wouldn't go linearize it?
You could not linearize it. So the question here was that if this was, instead of a plus minus 3 or plus 3, then I will stop right there. I will just say this is not a convex program. It's a piecewise linear program, but it's not a convex program. I won't go any further. It won't work. I know it won't work. But for this particular case, how would I linearize it now? What are the constraints that I'm going to put?
The absolute values for variables.
Well, I don't want to put variables. You can do it by variables, but without doing variables also we can do it. We've already introduced a new variable alpha. Yeah?
Can't you just move the other side? You'd have the absolute value of 2x plus 7x2 minus 3 less than or equal to, then you do everything to the other side, and then you have greater than or equal to negative everything to the other side. You just have to rearrange it.
Right. So another way of doing it is that since we like to keep all our variables on one side of the constraints or of the sign, I'm going to write this as two sets of constraints. 2x1 plus 3x2 minus 3 bracket 2x1 plus 7x2 minus 3 minus alpha must be greater than or equal to 0. Remember, when I did the linearization, alpha is a variable. It's not a constant. It's a variable. So I put it on the other side. And the other constraint I say is 2x1 plus 3x2 minus 3, the negative of whatever is in the bracket. So it's 3 minus 2x1 minus 7x2 minus alpha is greater than or equal to 0. So these two, this constraint and that constraint are both, so this set of constraint is equivalent to that constraint. Any questions? So let me repeat what I said. So if you want to look to see whether something can be solved by a linear program, check to see whether everything is piecewise linear. So you should have only piecewise linear functions. If the constraints are not piecewise linear, there is no hope. You can stop. In addition, you have to make sure that the problem itself, the optimization problem, is convex. If it satisfies both these conditions, you can solve it by LP. Otherwise, you cannot. So when you have a plus sign sitting up there, the function up there is not a concave function. Therefore, although it satisfies this part, everything is piecewise linear. It doesn't satisfy this part, so you cannot solve it by LP. Any questions on this story?
So should max concave function be solvable?
Yes. So when you don't have the plus sign up there, when you have a negative sign sitting here, with the negative sign, this function up there is, whoa. It would help to just shut off the phones before you enter the class. If you have a negative sign up there, it's a maximization of a concave function. We can do it. But if you have a plus sign up there, it's a maximization of a convex function. Cannot do it. Okay? So this is the rule that you need to use. But that's something I could not talk about when I was doing linear programming because we didn't know what convexity was. But now that we know what a convex optimization problem is, we can attach that to this idea of piecewise linear, which is what we knew then, and say that some things, it can only be doable if the piecewise linear function in addition is convex. All right? Okay. So that was a little detour into convex programming that I had forgotten to talk about. Going forward, we come to something called quadratic programming. This is what we'll be spending a lot of time over because this is something that you guys need for doing Markowitz mean variance portfolio selection. So so what is a quadratic program? Did you have a question back there? Any questions? Maybe the class could help, listen to the conversation. It might be better for them too. Okay. So what is a quadratic program? A quadratic program has two things. The objective is a quadratic function. Meaning that the power of any of the variables is at most 2. For a vector, a quadratic function can always be written like this. It's C transpose x plus x transpose qx, or vx in this case. So here's a function. Let's see if we can write it in that form. F of x is 2x1 plus 3x1 squared plus 7x1 x2 plus 9x2 squared. So I want to write it in this form. A vector C transpose x plus x transpose a matrix Vx. And one thing that's missing there, we'll show how this happens, and then we want a special property of that V as well. So how do I write it in that form? What is the vector C in this case?
2, 0.
2 and 0. So 2, 0 transpose the vector x. That represents the linear part of the function. What about for the other guy? So let's put the x1 and x2 over here. That transpose a matrix here, x1, x2. Do I put a half in front? No. Okay, doesn't matter. Let's put a half here. Makes life simple later on. So what's this matrix?
6, 8.
6,
That is 8.
8. How did you get 8?
Because you have 14. 18. 18. You have 47. You can put 7.
Yeah, 7. Okay.
18.
So here comes 18. And what I'm going to do is split up that 14, 7 and 7. So all I'm doing is, this comes from the fact that half of 6x squared can be written as 6 here with x1 squared and x1 squared, x1 and x1. The 18 comes from doubling the 9. From doubling the 7 you get 14. I could write that 14 any which way. I could write 14 and 0 or 14 and 0. It doesn't matter. But I'm going to split it this way because this time this matrix V is symmetric. Meaning that V is equal to V transpose. If I try the transpose of the V matrix, I get the same matrix back. It helps. Why does it help? Because symmetric matrices have real eigenvalues. From the point of view of actually using quadratic programming, it doesn't matter. But from the point of view of actually coding a solution to a quadratic program, it does matter. It does matter that the V is symmetric. So it's by convention, people always write it in a form that makes it symmetric because you can always do it. It doesn't stop you from anything. So might as well write something symmetric. So at the end of the day, what happens is that f of x, the most general f of x we can talk about, looks like this. C transpose x, the linear part, plus 1/2, that's by convention, x transpose Vx, where V is equal to V transpose. V is symmetric. I can always write the objective function in that form. So the objective is quadratic, but the constraints are linear. So that's a big thing to remember, that in a quadratic program, although we call it a quadratic program, we are only talking about the objective function. The objective function is quadratic, but we do not allow any quadratic constraints. If you have quadratic constraints, then it's called a quadratically constrained program, not a quadratic program. So you cannot use anything that you know about quadratic programs for quadratically constrained programs. Okay. What time do I have? Very good. Doing well. So one of the reason we're going to be talking about quadratic programs is because of this example, the so-called mean variance portfolio selection problem. So we'll be talking about this problem quite a bit, so let me formulate it now and see how things go. And then we'll talk about a little properties of quadratic programs before we go further. So the story here is that you've got n assets. And let's say that the return vector on these n assets, R, which lives in Rn, is normally distributed. Have you guys done multivariate normals before? Has it been done in the stochastic course or not at all? No. But have you seen multivariate normals before?
Univariate.
Univariate. Okay. So we're going to say that this guy has a multivariate normal with a mean mu and a covariance matrix, what did I call there? Sigma. What does that mean? It means that if you look at the density of this vector, it looks like 1 over 2 pi raised to the power n over 2, where n is a dimension, e to exponent of minus 1/2 x minus mu sigma inverse x minus mu. That's what the density looks like in multi-dimensions.
Should there be a transpose?
Oh yeah, the determinant of this guy down here. And there's a transpose here. So it's 2 pi n over 2 times the determinant of the matrix sigma raised to the half. Okay. Nasty looking function. The only thing that I ever want to remember about this thing is the fact that it looks like if it was one dimensional, then this f of r for one dimensional would have looked like 1 over square root of 2 pi sigma e to the minus or exponent x minus of x minus mu sigma to the minus 2 x minus mu divided by 2. So those would have looked similar, so I'm willing to believe that that's multivariate normal. The property that we would need for this application, and I'm sure Ward would cover multivariate normals at some point and give you much more information than you would ever want to know. But at this point what we care about is the following, that if R is distributed according to normal distribution, multivariate normal distribution with mean mu and covariance matrix sigma, and I create this inner product, R transpose phi. So phi is a vector, R is a vector, phi is a fixed vector, it's not a random variable, then that vector is also normally distributed with mean vector mu transpose phi. So all I did was I take the mean vector here and took its inner product with phi, and a variance which is given by phi transpose sigma phi. So this guy here is a one-dimensional normal, univariate normal. So for the purposes of my Markowitz problem, this is what I care about. I only care about the fact that if somebody gives me a multivariate normal distribution, it has this property that if I take the inner product of this multidimensional vector with some fixed vector phi, then I get a new random variable whose mean is mu transpose phi and whose variance, not the standard deviation, but the variance is phi transpose sigma phi. So what Markowitz suggested was that in order to select portfolios, what one needs to do is not just consider, so suppose you're given this information that you've got n assets with a return vector which is normally distributed with mean mu and covariance matrix sigma. The first thing that might come to mind would be to solve this problem. Maximize the expected value of R transpose phi such that phi or 1 transpose phi sums to 1. So if I've got $1 to invest, how should I spread it to maximize my returns? So this would become the LP maximize R transpose or mu transpose phi such that 1 transpose phi is equal to 1.
So what do you mean by n assets are normally distributed?
Okay. So the word normally here refers to the fact that if you look at this multidimensional vector, its density is given by this. That's what I mean by saying it's normally distributed. More than that,
Professor, it should be f of x equal to
oh yes, not R, X. So x is a vector in this case, x is a scalar in this case. So I guess to answer your question as to what do I mean, I just mean that that multidimensional vector has that density. And for the purposes of what I need it for, all I care about is that this vector, the return vector, is such that every time I hit it by a fixed vector phi, I get a one-dimensional quantity. So R transpose phi is scalar. R is a vector, phi is a vector, but R transpose phi is a scalar quantity. That scalar quantity is normal.
So I understand it mathematically.
Yeah.
But what are we doing in financial terms by doing all this?
Nothing. So in financial terms, all one is saying is that there is, okay, so in your stochastic course, you will at some point see this thing called the central limit theorem. So what the central limit theorem says is that if you took samples of this vector R, no matter what its distribution might be, assume that it has a second moment, and you average the returns that you got over a large period of time, then that average will start looking normal. And therefore, if you have a long enough time horizon, then you can start pretending that the returns that you're getting from the market are normally distributed. Choose your portfolio as if these things were normal, and then if you use that portfolio in the market, you have enough patience, you have enough deep pockets to actually sustain yourself for a long enough period of time, you will notice that it will give you normally distributed returns. If everything is, on the other hand, if you do not have deep pockets, at some point you'll go bankrupt and therefore it becomes useless. There are other ways of getting around it. People do these things called log returns and things of that sort, but the basic assumption behind Markowitz's problem is to say, well, if you have long time horizons and liquidity is not a problem for you, pretending that the market is normally distributed is a good first approximation. You can refine over it, but that's a good starting approximation. Before Markowitz came into the picture, this is what people were pretending to do. You say that I want to maximize the expected value of the return, subject to the constraint that I've got $1 to spend. Question?
Just what you want to do now is decide the level of return and then minimize the variance.
Yes, that's what Markowitz suggested. Markowitz is, so this was what the prevailing state of the art was. He said this doesn't make sense, because what is the optimum solution of this guy? You've got one constraint and you want to maximize a linear function on one constraint. What's going to happen?
Put all your money in one asset.
You'll put all your money into one asset, and therefore there is no way you can leverage out the fact that you've got multi-dimensions. There are correlations between assets which can actually reduce your variability by spreading out your money. So when people formulated this problem with just looking at linear constraints, you have this problem that you don't diversify. You put everything into one asset. What Markowitz suggested was that if you end up you transform that problem, and there's a typo here that I'll correct in a moment, is that you shouldn't just simply look at expected return. You should look at the second moment as well. Look at what happens when you try to insist that your return is up to a certain quantity, and among all those portfolios, choose the one that has the minimum variance. So his problem was the following. You want to minimize the variance, minimize the variability in your return, the variance in R transpose phi, the return that you're going to get, such that the expected value of the return is exactly equal to some quantity alpha, and that's what the typo is, it shouldn't be 1, and 1 transpose phi is equal to 1. So here, contrast it with this problem. The expected value of R transpose phi such that 1 transpose phi is equal to 1. Here you're only looking at first moments. You're simply saying maximize the expected value subject to this constraint. Here you're looking at a family of optimization problems. For every value of alpha, as you change the value of alpha, you get a different portfolio. For a fixed value of alpha, what is this problem doing? It's saying, find me a portfolio such that its expected return is equal to alpha, and among all those portfolios for which the expected return is equal to alpha, choose the one which has the minimum variance. As you change the value of alpha, you'll end up getting a whole collection of different portfolios. a collection of different portfolios which work for different values of alpha. And this whole story of efficient frontiers and other things that we are going to see, hopefully starting next week, works on what happens when you change alpha. Today, all I'm concerned about is for a fixed value of alpha, meaning this guy alpha is not a variable, it's a constant, how do I solve this problem? So by using the fact that phi, R transpose phi is a normally distributed random variable, this optimization problem is the same as minimize phi transpose sigma phi such that mu transpose phi is equal to alpha and 1 transpose phi is equal to 1. Question?
With increase in alpha, the variance will obviously increase. So,
Uh,
the one the variance should increase.
Okay, so the question is, if I increase alpha, should the variance increase? Yes, it will increase. The question is, would it increase at the same rate as the return goes up? If it so happens, so if I insist on more money, chances are you'll get more variability. But if the variability is, the rate of increase in variability is less than the rate of increase in the return, then it's probably good for me. And you'll get a profile based on what happens. And that's what we'll talk about when we talk about how this whole thing changes when alpha changes. Okay? So far all we're saying is that this is a quadratic program. That's all I'm worried about right now. Its objective is quadratic and its constraints are linear. And the reason why linear program or quadratic programs are good to solve, or something that everybody likes, is because the gradient of a quadratic function is linear. When we look at when we try to find optimality conditions, it typically will have an equation in terms of the gradient. You'll have something, gradient is equal to not 0 but something else. But for a general nonlinear program, this gradient is a nonlinear function. Trying to solve that is hard, but if it's a quadratic program, the gradient will become linear, so solving it is easy. Yes?
Does it make a difference if you said, instead of equal to alpha, if you said greater than or equal to alpha?
Well, it does make a difference, and the places it makes a difference is situations where this matrix sigma doesn't have full rank. The reason I've made it equal to alpha is because this is the exact formulation that Markowitz came up with. It makes a difference also in terms of trying to plot out various things. It becomes that you get a nicer plot by looking at alpha. If you make it greater than or equal to alpha, then it turns out that the plots are harder to interpret. But you can get the same information in the other one too. It's just harder to interpret.
I guess it just seems that if you're trying to do this from an investor standpoint, like if you can find a portfolio that's equal to alpha, and you find that this one that has the same variance that gives you a better alpha, you're going to take the one that has a better alpha.
True, but then I would argue that I'll give you this entire curve. You choose what variance you want, and I'll give you the best alpha for that. So the same information exists in both cases. It's just how you interpret it. Okay? Question?
Just that the assumption of normality, you don't use it in that problem.
In this problem?
Don't you just use that you have a covariance matrix?
Yeah, but what is the... I guess that's true. Absolutely true. But the thing that what would have... Okay, so the question is that in formulating this optimization problem, I don't have to care about what happens to the return vector. It can be anything. The reason I want to put normality on top of it is, at the end of the day, when I look at this on a multi-period and I look at what is the performance of this phi, it will look as if I'm looking at a normal random variable. If I fix the phi and look at returns coming out of it, it's as if the market is normal. But as far as this formulation is concerned, you're absolutely right. There is no reason to assume that R is normal. Okay? All right. So I'm going to skip this, and I'm coming directly to first order conditions, and then we'll see whether... Actually, what time do I have? Forget about this. We'll come back and cover this later on. Let's look at Lagrange conditions. Makes life easier, and let's go up to trying to solve this problem. So here's how things we'll finish up today's lecture by trying to solve an equality constrained QP. So let me just finish this list here. So quadratic program. So those are the 4 different programs that we're going to talk about in our class. We'll start with quadratic programs. That's the most of the time we'll spend on quadratic programs, move up to separable, and then show you some special cases of convex. So the simplest problem is something called an equality constrained QP. So that particular problem that we wrote up, which was minimize phi transpose sigma phi such that, what was it? Mu transpose phi is equal to alpha and 1 transpose phi is equal to 1. This is an example of an equality constrained quadratic program. Quadratic objective, linear constraints, but in addition, all constraints are equalities. There are no inequalities here. So equality constraints QPs are actually very nice. You can write the solution of these QPs out almost as a set of equations. And the way you solve them is through something called Lagrangian method. So what you do is the first step you construct something called the Lagrangian. I don't remember if I called it a Lagrangian when I was doing LP duality, but we constructed the same function at that time. So this function L looks like mu transpose sigma phi, the same thing that we had before. Let's put a half in front. It just makes taking derivatives easier. Phi transpose sigma phi minus a multiplier times this one. So let's call it V1 times mu transpose phi minus alpha minus V2 times 1 transpose phi minus 1. The signs of these multipliers are given by the same rules that were there for linear programs. We construct this Lagrangian using these multipliers for these constraints. Why do I make these multipliers? Because I don't like constrained programs. Constrained programs are annoying. I don't know what to do with them. So I want to get rid of all the constraints and somehow work with an unconstrained problem. In order to work with the unconstrained problem, what do? I multiply these by some penalty multipliers, V1 and V2, and add them to the objective. What will be the signs of these guys, V1 and V2 in this case, if you were using the rules? Question.
No, could you write a little bigger?
Little bigger. Okay. So V1 times the first one, which is mu transpose phi minus alpha, minus V2 times 1 transpose phi minus 1. So what will be the signs of V1 and V2 if we were using linear programming here?
Greater than equal.
Greater than equal to 0?
Greater than 0.
Greater than 0? So we can, okay, so linear programming rule said that every time you have an equal to constraint, that's an odd constraint. So its corresponding variable must be an odd variable. And what is an odd variable? A free variable. I don't care. So V1 and V2 are free. No restrictions on them. Okay? So that's a Lagrangian. Then what I do is solve it. Pretend as if this Lagrangian now is an unconstrained problem in phi. I fixed V1 and V2. I don't care about what they are. I just have made sure that they are free variables. So the second step is to minimize L with respect to phi. So if I take the gradient of that, what do I get?
You got a phi transpose sigma.
So you get sigma phi from the first term. What do I get from the second term?
Minus mu transpose phi.
Yeah, I'm going to put it in column vectors. So minus the scalar v1 times mu, and what do I get from the last one? Minus v2 times the vector 1. So what I'm doing here is I'm pretending I'm only minimizing with respect to phi. v1 and v2 are fixed scalars. I set this equal to 0. So in this step, it's not very complicated. The only thing that happened is that I have a vector function and I took its gradient. If you're not comfortable with doing this, write out the expression, and when you take the derivatives, you'll see that this is exactly what you're going to get. So if you move things around, this implies that sigma phi is equal to v1 mu plus v2 1, the vector 1. Now I'm going to make the assumption that this matrix sigma is invertible. So if I make the assumption, what does that physically mean, that the sigma is invertible?
It's full rank.
Okay, at least it's a square matrix. What else?
It's full rank.
It has full rank, but physically what does it mean in terms of this application? What would a full rank covariance matrix mean?
It's independent.
Yes? Anybody?
They're not correlated.
They are correlated. They are correlated. Otherwise, there is no otherwise it's a diagonal matrix. But none of the assets are perfectly correlated. You cannot reproduce one asset's return by looking at a combination of other assets. A covariance matrix that has full rank means that the randomness is full dimensional. The assets live in a full n-dimensional space, which means that you cannot replicate one asset by looking at a combination of other assets. So typically in the real life, when you have S&P 500, which has got 500 assets, or Russell 2000, which has 2000 assets, the covariance matrix is not full dimensional. You don't expect 2000 sources of randomness in the market. So what people do is construct factors. So for those of you who have seen some principal component analysis, you try to solve the same problem along the principal components rather than looking at the full covariance matrix. If you don't know what I'm talking about, just completely ignore this statement. You will eventually learn it in the data analysis class, which comes, I think, probably in the fall or in the spring. So until then, just pretend that I never said it. Okay, so this is equal to sigma phi, which means that my vector phi, the portfolio vector phi, is simply v1 times sigma inverse of mu, this vector, plus v2 times sigma inverse of the 1 vector. So given the multipliers v1 and v2, I know exactly what phi is. Phi is given by this question, by this particular relationship. Now how do I find v1 and v2? I put it back into the equations. This phi must satisfy these constraints, which we had completely ignored. So I plug it back in there. From the first constraint, I end up getting v1 times mu transpose sigma inverse mu plus v2 times mu transpose sigma inverse 1 must equal alpha. I've just plugged in this phi into the first equation over there. The second equation tells me that v1 transpose times 1 transpose sigma inverse mu plus v2 times, this thing is going completely down, so let me just flip it over. So here are the equations once again. v1 times mu transpose sigma inverse mu plus v2 times 1 transpose sigma inverse mu must equal alpha. v1 times 1 transpose sigma inverse mu plus v2 times 1 transpose sigma inverse 1 must equal 1. So that I get by plugging the phi into the two equations that I have. Two equations in two unknowns, I can solve it. I get my v1 and v2, I plug it back into this expression for phi, I know the portfolio. So to return back to the question, So what are the steps? The first step is just construct the Lagrangian. For an equality constraint problem, that's simple. You just subtract out the constraints, don't care about what happens to V1 and V2 because they are free. Compute the gradient, set it equal to 0, solve for the variable phi, and once you get the variable phi in terms of the multipliers V1 and V2, the feasibility conditions tells you what V1 and V2 must be. Alright, so this whole setup is actually pretty simple to do. The question that still remains is, why does it work? Why do I even, this just looks like something I pulled out of my hat and said, fine, do these steps. At the end of the day, I got something. There is no reason to believe that that something is anywhere close to even being locally optimum. Forget about being globally optimum. I don't even have a guarantee that this phi is locally optimum. Once I have figured out that it is locally optimum, I still have to argue that it is globally optimum. So let's try to answer that question. Suppose this phi that I've constructed from here is locally optimum. Will it be globally optimum for this problem?
Yes.
Yes. Why?
Because you have a convex problem with a convex set.
So the convex problem assumes that you have a convex set. But why is this problem a convex problem? So it's got a convex feasible set for sure. It's got linear equations. That's a convex set. What about this function? Well, linear, therefore it's convex. What about the function? Function is non-linear.
It's a convex function.
Why is it a convex function?
It's quadratic and
Quadratic need not be convex, because the quadratic minus 2x squared is certainly not a convex function. The Hessian of that particular function is sigma, and sigma is positive definite. Why is it positive definite? Or at least in this particular case, why does it have to be positive? At least it has to be positive semi-definite in this case. Why is that?
Because it's a covariance.
Because it's a covariance matrix. It's a covariance matrix. Covariance matrices by definition are positive semi-definite. Therefore, this objective function is a convex function over a convex set, convex optimization problem. So if I can show you that this fellow is a local minimum, I'm done. So that's a story that we will take up on Tuesday morning, or sorry, not Tuesday morning, Thursday morning, and try to show you how that works. But the things that I want you to take away from the story of today is these 4 different kinds of nonlinear programs that we are going to worry about. And the other story that I want you to take away is that if you've got an equality constraint QP, it's trivial to solve. It's something that can be done very quickly and very fast. There was a question asked earlier, why did we not make this an inequality? The answer, one thing is that it's, you would probably end up getting the same problem, but the other issue is that if this is an inequality, then I have to worry about the signs of V. And if I had to worry about signs of V, I cannot do this process very easily. So on Thursday, we'll see how one can take an inequality constrained QP and reduce it to an equality constrained QP and work from there. Question?
When's the assignment due?
Well, it all depends on you. When is the assignment due? Are you willing to turn it in tomorrow in the recitation?
Can we turn it in at a later time, maybe in the day?
The recitation ends at 6:30. I'll be home after that.
No, the only problem is that the whole day we're in class, so that means essentially we're turning it in tonight.
Well, let's take a vote. Who's willing to turn it, and how many of you want to turn it on Thursday? All right, so it looks like about half the class wants to go Thursday and half the class Wednesday. And since the due date was Thursday, we'll stick to Thursday. Well, you've got recitations before that.